We're going to continue on with the Chapter 2 notes, specifically about naming stuff. And the main thing of this part, well, not this very beginning of this, but of naming, this is also known as chemical nomenclature. You'll see that term a lot, chemical nomenclature. The term nomenclature just means the system of naming. How do we name this stuff? Okay, how do we name molecules? How do we name ions is the main thing. So molecules and ions is what we're going to be talking about. So what in the world is a molecule? Molecule, it's an arrangement of two or more different atoms defined in a definite arrangement held together by chemical bonds. Hydrogen, water, this thing's called ammonia, methane. I know you probably you don't know these chemical formulas yet, but water you've heard of. It has a definite arrangement. There's 2 hydrogens for every 1 oxygen. In ammonia, which is a cleaning solution for most of us, there's 1 nitrogen molecule, or 1 nitrogen atom, sorry, not molecule. 1 nitrogen atom for every 3 hydrogen atoms in the molecule of ammonia. In methane, CH4, there's 1 carbon atom for 4 hydrogen atoms. They are arranged together, and this is we have not done the molecular geometry chapter because this is only still the first few weeks of chemistry. But the molecule shape looks like this, and we'll get to one day why the shape of water molecule looks like this bent structure. But a molecule, 2 or more atoms together, held together by some sort of chemical bonds. There's 2 things of molecules. They're either considered diatomic, prefix di for 2, meaning there's only 2 atoms in it total, whether the same 2 atoms, N2, O2, Br2, or 2 different atoms like carbon monoxide, CO. Okay, but there's just 2 atoms total. H2 there, 2 atoms total. We also have polyatomic molecules. There's more than 2. There's no I guess there's a word for triatomic. I just made it up right now for 3 atoms. We don't call it, we just say poly. Anything that's more than 2 atoms is polyatomic. Many atom, like polygon. Polygon is it's a gon with many sides. It's a many-sided figure. Okay, poly meaning just many. Okay, so next. Okay. An ion is an atom or group of atoms that has an overall net or positive charge. So an ion could be there's 2 types of ions. Maybe I should show this whole slide. There's 2 ions, positive ones, and there's negative ones. I'll just put myself so I'm not blocking too much of the screen anywhere. That's worse. Okay, so there's positive ones, and those are called cations. And there's negative ions, also known as anions. Cations have an overall positive charge. Anions have an overall negative charge. And why in the world does it have a positive charge? If a neutral atom loses 1 or more of its electrons, it becomes a cation. We'll get to why it loses an electron, but sodium atom has 11 protons, is element number 11 on the periodic table, and it has 11 electrons. If it were to lose 1 of its electrons, it'll have 10, meaning there are more protons than our electrons, which makes it overall a positive charge. We represent that by putting on the top right here a plus sign that says it's a positive charge. If something gains an electron, it'll have an overall negative charge. If a neutral atom gains 1 or more electrons, it becomes an anion. Oh, notice it pronounced anion, cation, not anion or cation. Okay. Chlorine is normally 17 protons, 17 electrons, but if for some reason it gains an electron, it'll have a total of 18 electrons. More negative, electrons are negative, more negative than are positive, giving the overall negative charge. We put a minus sign to represent the negative anion. So positive cation, negative anion. Okay, going on. So monatomic ions is an ion that has only 1 atom. These are monatomic. Notice 1 atom ions. We also have something called polyatomic ions. Has more than 1 atom. Here are examples of polyatomic ions. OH minus, which is also known as hydroxide, is a -1 charge. That means it gains an electron somewhere. We'll get to why later. Cn minus, also known as a cyanide ion. Carbon, nitrogen together gains 1 electron. NH4 plus, also known as the ammonium ion, lost one of its electrons, became positive. NO3, also known as a nitrate ion, gained an electron. That's why it's -1. So here, sodium plus positive means it lost an electron. Negative means it gains an electron. Here, Ca2 plus means it lost 2 electrons. O2 minus means it gained 2 electrons. Al3 plus means this thing has lost 3 electrons. N3 minus means it has gained 3 electrons. Now, how do I know the charges of these? There's actually a table. I think I might have to jump way ahead to the table for a second. I'm going to skip that for now. I'm going to jump to the table. That's much later on in the notes. I'm sorry. There it is. Here's a table 2-3 in the notes that has a list of all our different ions. And so you'll see like aluminum ion. This is just alphabetical. Cation positive, anion negative. Aluminum 3 plus. Aluminum loses 3 electrons. Barium loses 2 electrons. Cadmium loses 2. Calcium loses 2. Cesium loses 1. That's why +1. Bromine gains an electron. That's why -1. Chlorite gains an electron. Hydrogen gains an electron. Fluorite gains an electron. Iodide gains an electron. But those, I was just pointing out some of the monatomic ones, one atom ones, like barium, cadmium, calcium, cesium. But notice all these polyatomic ones, like carbonates. CO3, 2 minus. The entire CO3, this is not 3 negative 2s. The entire CO3 has gained 2 extra electrons. The entire molecule, or polyatomic ion, has a -2 charge. Chlorate ion, ClO3, the entire thing has gained 1 electron. Chromate, CrO4, the entire thing gained 2 electrons. Down here, nitrate, NO3, the entire thing gains 1 electron. Normally, I would have you guys memorize all these ions. Yes, it's annoying, but that's really what you would normally have to do. Kind of like in elementary school in 3rd grade, you had to memorize the periodic table. In this class, you should have memorized the elements. I don't know how I'm going to test this, but I'll figure it out later. You technically should have will one day should have memorized it. Cn minus, Cn is called cyanide, and that's a -1 charge. Cr2O7 is called the dichromate ion, and has a charge of -2. Versus the chromate ion, which are CrO4 with a -2 charge. These are things that technically you should memorize. In case you're like, oh my goodness, that's a lot of them. Yes, there are a lot. In terms of these common inorganic polyatomic ions, I believe there's only like 20-30 of them. I know that's not 2, but 20-30 of them is not that bad. Okay? So, but 20-30, complicated ones is not like a list of 100 complicated ones. But there's no shortcut around it. Honestly, it's just memorize that. When I see Cn, I kind of know that's cyanide, and it has a charge of -1. You also notice on the positive side cations, there's some that say iron 2, iron 3 in parentheses. They're Roman numerals. It's called the stock system. We'll get to what that is. But we'll be using this iron 2, which means iron plus 2. Iron 3, which is iron plus 3. Lead 2, which is lead plus 2. Or mercury 1, oh, well, okay, that's a weird exception. Chromium 3, which is chromium plus 3. This other term, chromic, cobaltous, cuprous, cupric, ferrous, ferric, plumbous, those are called the classical names. We won't be using them, but they are still around. These were known as classical names. But cobalt 2 is known as cobaltous. Cobalt 2 is cobalt plus 2 charge. Okay, let me go way back where we left off. Okay, back here. This is where we left off. Okay, so monatomic ions, it's on the table. Polyatomic ions, 2 or more atoms, they're on the table. And you should theoretically one day know that NO3 is called the nitrate ion, is charged as -1. NH4 is called ammonium ion, is charged as +1. CN is called the cyanide ion, is charged as -1. OH is called the hydroxide ion, is charged as -1. And the only way you know that, the 20, 30 of them, is to memorize them. And it's not that many. It's like 20, 30 of them. It's not that bad. Okay, so I think we understand ions. If so, I'll go through the first one. I'll ask you questions on the second one. How many protons and electrons are there in aluminum 27 plus 3 ion? Okay, protons is actually easy. It's the bottom number, 13. Okay, remember atomic mass number on top, atomic number on bottom. Mass number on top, atomic number on bottom. Mass number on top, atomic number on bottom. Atomic number is the number of protons, 13. So number of protons is 13. Before we said number of electrons equals protons. That's if it's neutral. This one is not neutral. This is 3 plus, meaning it lost 3 electrons. If it normally has 13, but it lost 3 electrons, what's left? If it normally has 13, but it lost 3 electrons, it will have 10 electrons left. It doesn't ask, but how many neutrons are there? 27 minus 13. Or what is that? 14 neutrons. Okay. One more. How many protons or electrons are in selenium 78 minus 2 charge? So, well, how many questions are there? Or sorry, how many protons are there? Well, this is the bottom number again, 34. How many electrons? Notice it's not neutral. There are 2 more electrons. Minus 2 means there are 2 more electrons than are protons. If there are 34 protons and there are 2 more electrons than protons, we'll have a total of 34 plus 2, or 36 electrons. If the question asks how many neutrons, subtract 78 minus 34, which, what is that? 44 neutrons. They didn't ask. I'm just asking separately. Okay, if we took all those ions on that other table and I put them on a periodic table, you probably actually will see a pattern. You'll see a pattern that, hey, lithium, sodium, potassium, rubidium, cesium, francium, which is also, it's not on that list, but it's there, all have a +1 charge. Alkali metals have a +1 charge. Hydrogen's not technically alkali metal. It's not even a metal. The alkali earth metals, the group 2 elements, beryllium, magnesium, calcium, strontium, barium, and what's that? Radium underneath, even though it doesn't say so. It's a +2 charge. Halogens, fluorine, chlorine, bromine, iodine, fluorine, chlorine, bromine, iodine. I'm losing it. I don't remember right now what the other one is. But whatever it is on a periodic table, I'm just losing it right now. Halogens are -1 charge. Oxygen group overall are -2 charge. Oxygen, sulfur, selenium, tellurium, whatever is underneath, -2 charge. So there's some elements that we actually do know their charges. The first 2 groups and group 16, 17 groups, we know their charges. Noble gases don't form molecules. They are stable molecules, or stable atoms, not molecules. Stable atoms that don't really react. So in general, noble gases will not be in any of our molecules. Okay, so in this chapter, I'll put my face down here. In this chapter, we're talking about just the molecular formula. We're just be talking about molecular formula. In a later chapter, we'll talk about structural formulas, also known as Lewis dot structures, if you've heard that term before. If not, that's a later chapter on how are they all connected. And then we'll talk about the molecular geometry, the shape of the molecules, although you know how they're connected. It's not necessarily like that, but like these, what's called ball and stick models. Again, a much future chapter. And this is reality, how they look like based on their size. So in this chapter, though, we're going to just talk about molecular formulas. Okay, in a molecular formula, it will show us the exact number of atoms of every element in the smallest unit of the substance. Like water, H2O, 2 hydrogens for every oxygen. They probably will also be written as an empirical formula, which shows a simplest whole number ratio of the atoms in the substance. Actually, they shouldn't They don't always have to be, but empirical formula is the smallest whole number ratio of this stuff. Examples. Water, H2O, it is already its empirical formula. It's already the smallest ratio, 2 to 1, 2 hydrogens for every oxygen. If I have an glucose, C6H12O6, anyone who's taken biology will probably recognize that's glucose, simple sugar. There's 6 carbons to 12 hydrogens for every 6 oxygen. The ratio is 6 to 12 to 6 in its empirical formula, same as 1 to 2 to 1. It's like ratios that you do within your algebra class. 6 to 12 to 6 the same as 1 to 2 to 1. The only tricky ones are anything that's an element by itself. An element by itself is just an element. And one more example. Molecular formula C2H4. Its empirical formula 1 to 2 or NH2. That's it. Empirical formula. 2 to 4, same as 1 to 2. Okay, so let's get into how do we write chemical formulas and stuff. Ionic compound of salt. This is just a picture of salt crystals there. Yes, they're actually cubes. If you looked under a strong magnifying glass, you could probably actually see cubes in it. Okay, so ionic compounds is a combination of cations and anions. Okay, positive and negative. You will not have 2 positives. You'll not have 2 negatives because opposite charges attract, like charges repel. So for us, we'll always only have something positive and something negative. A cation and an anion. Few things about ionic compounds. They will always be written as empirical formula. Salt, in this diagram here, you'll probably say, oh, I see about 100, I'm not counting, I'm just making it up. There's 100 sodiums, there's 100 chlorines. Don't say Na100, Cl100. It's always in the empirical formula, the smallest ratio. There's 1 sodium for every chlorine, 1 sodium for every chlorine, 1 sodium for every chlorine, 1 to 1, NaCl. Not 100 sodiums for 100 chlorines. Always in the smallest whole number ratios. And this is actually an important part here. The sum of the charges of the cation and anions of each formula unit must equal 0. The total charges must equal to 0. The charge of sodium, if I went to that table for the charge of sodium, is positive 1. The charge of chlorine is negative 1. So the sum of the charges, positive and negative, positive 1, negative 1, must equal to 0. If it does not equal to 0, technically, it's not correct. The sum of the charges must add up to 0. Let's look at these chemical formulas. These are actually correct chemical formulas. This one is called aluminum oxide. You're like, aluminum oxide? Shouldn't that just be ALO? Aluminum's Al, oxygen is O, ALO is aluminum oxide. Well, there's one thing you need to know, the charges of them. You would actually have to look on the table for the charge because you haven't memorized it yet. The charge of aluminum is positive 3. The charge of oxide is negative 2. It's on the table, which I'll show you a little later again. Aluminum's charge is positive 3. Oxide's charge is negative 2 from looking at the table. Right now, you don't have to memorize, so I'm just telling you it is. But the total charges have to add up to 0. Since I have 2 aluminums, each one is positive 3. I have 2 aluminums, each one is positive 3. That gives the aluminum a total of positive 6 charges. Oxygen. Each oxygen is a minus 2 charge. I have 3 of them. 3 negative 2s is a total of negative 6 charges. So the total charge of aluminum, positive 6. Total charge of oxygen, negative 6. The total charge adds up to 0. The formula of aluminum oxide is Al2O3. So not ALO. Otherwise, aluminum being positive 3, oxygen being negative 2, that would not add up to 0. Okay, look at the next one. Next one is called calcium bromide. We'll be naming them later. Calcium, if you looked on the table, is a positive 2 charge. Br is called the bromide ion. It's a minus 1 charge. So you can kind of figure out why its formula is CaBr2. I have 1 calcium having a positive 2 charge for positive 2 total. I have 2 bromines. Each one is negative 1. I have 2 bromines. Each one is negative 1. giving me an overall -2 charge. +2, -2 adds up to 0. Chemical formula calcium bromide is CaBr2. I'll be doing a lot more of these when I can write on paper. I can't do this while I'm using these notes at the same time. Okay, another one. This is called sodium carbonate. Sodium is +1 if you look on the table. CO3, don't actually look up. I'm not even sure carbon's on the table. And oxygen, we're not looking at. It's a CO3. It's one of those special polyatomic molecule. So one of those special, like 20-something special molecules. It's called carbonate ion. The charge of carbonate ion, the entire CO3 is a -2 charge. The entire CO3 is a -2 charge. Well, I have 2 sodiums, each one being +1, gives me overall +2 charge. I have 1 carbonate. The entire carbonate is -2 charge. So it's total -2. Correct formula sodium carbonate is Na2CO3. So that's how I write chemical formulas of ionic things. Okay, we don't need that right now. Okay, so how did I know that carbonate was CO3 -2? It's right here. Carbonate, if I can use the mouse, it's kind of hanging. Okay, carbonate, CO3 is charges -2. And I think that last one was sodium. Oh, sodium's just got cut off here. But other things we had, like aluminum oxide. Aluminum is charges +3. Oxide on the second column, -2. So aluminum oxide, going back, aluminum +3, oxygen -2. That's why it's formula aluminum oxide Al2O3, not just ALO. We have to look at the table. And this table, I think it's page 45 in the textbook, if you have the textbook. This one is cut off, okay? But this is page 45 in the textbook, the list of common inorganic cations positive and anions negative. Okay, how do we name it? Term, nomenclature. How do we name this stuff? First of all, it's always a metal and a non-metal in ionic compounds. And the second part, the anion part, or the non-metal part, the suffix is changed to I. I don't bother with that. I just name, there's always going to be 2 parts, a positive part, cation, and a negative part, anion. If I'm trying to name this thing, BaCl2, Ba is we always write the positive thing first. What is the name of Ba, and what's the name of Cl? Go back to the table. What's Ba called? It's called barium. What's Cl ion called? It's called chloride, right there, chloride. BaCl2 is called barium chloride. We do not say barium dichloride. We'll be using prefixes for something else later, but we do not use prefixes for this. K2O. What is K called? What is O called? Let me go back to the table. Hopefully it's on there. K is right here, potassium. O is right there, oxide. The name of K2O is called potassium oxide. That's it. MgOH2. Look up you know it's magnesium. Okay, so we'll look up OH. I know it's going to be called magnesium, whatever OH is called. Let me go back to that table. Magnesium, whatever OH is called. OH is right here. It's a special name. It's a polyatomic compound called hydroxide. OH is called hydroxide. MgOH2 is called magnesium hydroxide. Oh, I should mention about why is there a parentheses around it. Magnesium is +2, hydroxide is -1. For it to balance out, I need 2 hydroxides. Normally, it's like potassium, 2 potassiums, so I just put a 2 there. When I say I have 2 hydroxide, since hydroxide's polyatomic, I have to put a parentheses around it, and then I put a 2. This does represent 2 O's and 2 H's, but don't distribute this thing. Don't write MgO2H2. It's not technically incorrect. I mean, it is. You're technically correct, but when we have polyatomic ions, we don't distribute this thing. We just say, this is magnesium, and I happen to have 2 hydroxides. OH is called hydroxide. OH is called hydroxide. If you put O2H2, 1, it looks confusing. And 2, I don't know what in the world O2H2 is, but I know OH taken twice is called. That just happens to be 2 hydroxides. Okay, KNO3, K is potassium. NO3, let me go back to that table. NO3, right here, right there. NO3, which is a -1 charge, is called the nitrate ion. NO3 is called the nitrate ion. KNO3 is called potassium nitrate. So naming the stuff, it's actually pretty easy. You name the first part, you name the second part, you name the cation ion, you name the anion. How do I know the name of the cation anion? Cation anion. Look on the table on page 45 in the textbook. Cation, anion, cation, anion. +1, cation, -1, anion. That's how I name all the stuff. Okay, the only tricky thing is some cations have more than 2 charges, like iron 2, iron 3, copper 1, copper 2, cobalt 2. And which kind of things have more than 1? Those are actually transition metals. Will have more than 1 charge. So if there's a transition metal, we have to indicate the charge of that transition metal with Roman numerals. So, like, this is iron something chloride. You're like, iron chloride. Well, okay, let me go back to that table. Iron. Where is it? Oh, I see iron. Oh, wait, but there's 2 irons. Which one is it? Iron 2 or iron 3? I don't know. Oh, well, let's look at chloride at least. Chloride is a -1. Notice chloride is -1. Let me go back to that question. Chloride is -1. I have 2 chlorides. I have 2 chlorides in there, and it's -1. So that's a -2 total. If chloride is -2 total, that means the iron must be +2. Remember, total charges must add up to 0. So in this case, this is the iron with a +2 charge. I'm going to indicate the charge of that metal in Roman numerals. This is called iron 2 chloride. We will do this for all transition metals. Here's a different one. Oh, what's that? Well, remember, I know chlorine is -1, and I have 3 chlorines. So that's a total of 3 -1s, or -3. So iron's charge has to be +3 in that case. +3, -3. It's also known as iron 3 chloride. So you see the difference between iron 2 chloride, iron 3 chloride? It does not mean there's 2 irons or 3 irons. The charge of the iron there is +2. The charge of the iron there is +3. Here's another one. Okay, chromium is a transition metal. So it's going to be chromium something S for sulfide. If I look on the table, I'm not sure if it got cut off, but sulfide's charge is -2. Let me bring it up. Nope, it got cut off. Okay, but it got cut off, but sulfur's charge is -2. Okay, even though I got cut off there. Sulfur's charge is -2. I have 3 -2, so -6 total. That means chromium's charge has to be +6 total. But I have 2 chromiums. Total charge has to be +6. Each chromium must have a +3 charge. So the name of that thing will be called chromium 3 sulfide. So if I name ionic things and there's a transition metal in it, I must figure out the charge of that transition metal and then put the charge in parentheses and then name the other part, the anion. Okay, so that's how I name it if there's a transition metal. Now, let's get to another thing where, okay, let me move my face because we'll need to see that table. I'll show you the whole slide, it'll be easier. Oops, too far. Okay, so molecular compounds. So we're talking about all molecular compounds before. There's ionic compounds. Now there's molecular compounds. You might actually know these as covalent. Okay, but the term is molecular. They're made up of nonmetals and nonmetals together. So if I have 2 nonmetals, they're molecular. If there's a metal in it, it's ionic. Actually, that's a key thing. 2 nonmetals in it, maybe a metalloid. 2 nonmetals in it, molecular. If there's a metal in it, it's ionic. All nonmetals, molecular. A metal in it, it's ionic. How do I know metals and nonmetals? I have to go back to that other table. Actually, I'll just go back. It's quite back in the notes. Hold on 1 second. Even before that. Okay, here it is. The green elements are metals. The blue elements underneath all that are nonmetals. So if you had like sodium chloride, sodium's a metal, chlorine's a nonmetal, it's ionic. If you had two nonmetals together, like sulfur and oxygen would be molecular. If you have two nonmetals together, two blue ones, notice hydrogen's a nonmetal. If I have two blue ones together, or maybe a gray one on there, then it's molecular. The moment there's a metal in it, it's ionic. So if there's a metal in the substance, it's ionic. Two nonmetals, maybe a metalloid, or metalloids in between, literally. So two nonmetals, it is going to be molecular. Okay, now let me go way back again. Sorry. So that's just a review about how do I know ionic versus molecular. Molecular compounds, only nonmetals in it, maybe a metalloid. Okay, some have common names like water and so forth. Water and ammonia, but besides that, we're talking about how do we name this stuff. Well, first of all, how do I know which element goes first? Like carbon dioxide, why not dioxide carbon? Why is it carbon dioxide? We always put the element that's furthest left on the periodic table first. I don't have a periodic table in front of me without going all the way back in the notes, but carbon is further to the left than oxygen on the periodic table. We write carbon first. If it's oxygen and sulfur, which one comes first? I don't have a periodic table in front of me. Oxygen and sulfur so happen to belong in the same group. The element closer to the bottom of a group is the first element. So if I have sulfur and oxygen, sulfur just happens to be below oxygen in the periodic table, that element would be written first. And if more than one compound can be formed from the elements, use prefixes to indicate the number of each kind of atom. Here are the prefixes that you should know. Mono is 1, di is 2, tri is 3, tetra 4, penta 5, hexa, hepta, octa, nona, deca. 5, 6, 7, 8, 9, 10. We also change the last suffix to I. There's only one thing that we don't change at the prefix for. The very first element, if it is just one of them, we don't need to say mono for the very first element. But if there's only one element of the second element, yes, you will need to do mono for the second one. What? Let's just look at a whole bunch of examples. HI, not high. The name of that thing is hydrogen monoiodide. Hydrogen with one iodine. Hydrogen monoiodide. Mono for one. Mono, one. Hydrogen monoiodide. You don't need to say monohydrogen. You don't have to say mono for the very first element. That's the only one you don't have to use prefix for. This one, NF3. N is nitrogen. F is fluorine, but it'll be I, fluoride. Nitrogen, something fluoride. 3 fluorides, nitrogen trifluoride. SO2. What's the name of SO2? S is sulfur. O is oxide, well, oxygen, suffix changed to I, oxide. That thing is sulfur dioxide. N2Cl4. The prefix for 2 is di. The prefix for 4 is tetra. So this will be dinitrogen tetrachloride. Next one, NO2. Nitrogen with oxide. There's 2 oxides. Prefix for 2 is di. The name is nitrogen dioxide, which is a very toxic gas. If you breathe it in, it would kill you. But if it was N2O, that's 2 nitrogens, dinitrogen monoxide. You have to say there's 1 oxygen. Dinitrogen monoxide. If you breathe that in, that's laughing gas. It's also used to help calm people down at a dentist's office. So if you're a dentist's office and you ask for, because you forgot chemistry, you said, I feel nervous, give me some nitrogen dioxide. Maybe your dentist won't like you. And I'm kidding. But of course that's wrong. Nitrogen dioxide is a toxic gas. Dinitrogen monoxide is the laughing gas, or the gas they give you in a dentist's office that calms people down. Okay, I believe this is our last slide for today. This is kind of a summary of, and this is also in the textbook, of how do we name compounds. The very first thing we need to know, is it ionic or molecular? Ionic or molecular. And how do I know it's ionic? It has a metal in it. Oh, one exception to that, ammonia ion, NH4+, that's one exception. Because technically nitrogen and hydrogen are all nonmetals. But if it's a metal in it, it's ionic. If it's made up of only nonmetals, or a metalloid, it's molecular. Molecular, we use prefixes for both elements, except we could skip mono for the very first element and change the suffix of the second thing to I. That's all these examples. Nitrogen trifluoride, sulfur dioxide, dinitrogen tetrachloride, nitrogen dioxide, dinitrogen monoxide. Notice they all have prefixes, except for the very first element. If it's mono, that is. Okay, what if there's a metal in it? It depends. Is there one charge or more than one charge? If there's only one, if the ones that have more than one charge, the transition metals. There's a few exceptions, but transition metals have more than one charge, and not transition metal has only one charge. If there's only one charge, you just name the cation, you name the anion. How do I do that? Look on the table on page 45 that I showed you the list of ions. Name the first part, name the second part. That's how we name ionic compounds if there's only one charge. If there's a transition metal in it, meaning there's more than one charge, you say the name of the metal, figure out what the charge of the metal is in Roman numerals, and you put that in parentheses, and you name the second part. So this is just a general summary of how do we name compounds. That's why this chapter, big thing, is called chemical nomenclature.